atomic radius. Right? Okay. So the thing is like this. So basically, right, one may think that calculation of the atomic radius is easy, the like the definition, right? So what is the definition? First of all, definition is the atomic radius is the distance between the nucleus and the valence shell. That is the atomic radius, no? One can say, right? This is the atomic radius, no? Distance between the nucleus, center of the atom, to the end of the atom, to the center of the atom to end of the atom. At the center you have the nucleus, right? This is the atomic radius as a definition, right? But the thing is, practically, right, calculating the atomic radius or coming up with the atomic radius is a bit hard. Why is that? Because the atoms are not having these kind of boundaries. Atoms are not having this kind of, right, boundaries. Actually, atoms are not hard spheres like Dalton said. Like Dalton said, atoms are not hard spheres. Not like Thomson said, plum pudding with his plum pudding model. Atoms are not hard spheres. We know, nowadays we know, with the atom, we have a cloud model. We have a cloud model. So atoms are not with, right, finely, right, extracted boundaries. Right? So atoms are not with such kind of exact boundaries. Right? If you are to think of hard spheres, we can think of exact boundary with those atoms. But atoms are not like that. With the cloud model, right, you don't have definite boundaries. Atoms are not with definite boundaries. So that, yes, you have a center, but the boundaries not clear. With the atoms, the boundary is not clear. The final electron density is diffused. The boundary is not clear. So that calculating the atomic radius is much harder or can't be done by considering a lone single atom. By considering a lone single atom, you can't come up with the atomic radius. That can't be done because you don't have finely defined boundaries for the atoms as you are dealing with a cloud model, right? So we have problem. So actually what we are doing here is to come up with the radius or the size of the atom. What we are doing is, right, we take kind of closely connected atoms. Basically we can think of solid state particles, solid state substances. We can take the solid state substances where the particles are, where the atoms are closely connected to each other. Then what we can do is we can take the distance between the two nuclei of atoms. We can take the distance between two nuclei of atoms and we can divide that into two. We can divide that into 2 by 2 and take the value as atomic radius. That is what we are doing, right? As we don't have finely defined boundaries with the atoms, what we are doing to calculate the atomic radius is actually we take the solid form of substances, basically where the atoms are very closely connected, and then we take the distance between the two nuclei of closely related atoms, connected atoms, then we will divide that distance by 2 to come up with the atomic radius. That is how we practically obtain the atomic radius, right? Okay, that is this concept, right? That is how we practically obtain, right? So let's go to the note and we'll complete the note there, right? Okay. So it is said that like this, atomic radius and variations, it is said, atoms are not hard spherical objects as many of us think. Atoms are not hard spherical objects as many of us think. According to the quantum mechanical model, the cloud model, atoms do not have sharply defined boundaries. Atoms do not have sharply defined boundaries, so that we can't think of a isolated one atom to come up with the radius. Right? That is the reason, right? So based on the distances between atoms in various situations, based on the distances between atoms in various situations, we can define atomic size in several ways. Basically, here we are coming up with three different methods of defining the atomic radius. Three different methods, right, of defining the atomic radius. Anyway, with all these methods, this is the simple idea we are coming across. With all the three methods, the metallic radius, covalent radius, as well as with the van der Waals radius, with all the three concepts, this is the simple idea we are coming across, right? We just take the solid form, or we just take the atoms with their closest arrangement, nearby arrangement, and we take the distance between the two nuclei of two adjacent atoms, and then take the half of that value as the atomic radius. That is the normal practice, right, followed by all the three methods, right? The metallic radius, covalent radius, as well as with the van der Waals radius, right? We'll discuss one by one. The first point, the metallic radius, right? So metallic radius. So basically, in metals, so in our period table, we have three kind of atoms. No? In our period table, we have three kinds of atoms. At the left corner, basically with the S block and D block, we will see the appearance of metals. Metal atoms are there. Sodium, magnesium, potassium, zinc, copper, lead. Those are metal atoms. In our period table, we come across metal atoms, as well as non-metal atoms. Chlorine, oxygen, nitrogen, those are non-metals, right? And noble gases are also there. So various kind of atoms are there. So for metal atoms, to come up with the radii of metal atoms, we go for a concept known as metallic radius, right? To come up with the radius of metal atoms, we go for a concept known as metallic radius. To come up with the radii of non-metal atoms, we are using two techniques called as covalent radius as well as the van der Waals radius. Those are the three techniques we are following to come up with the atomic radius. For metal atoms, we use the metallic radius concept. For non-metal atoms like oxygen, chlorine, nitrogen, hydrogen, the non-metals, we use two concepts, covalent radius and the van der Waals radius. We'll discuss why two concepts are needed for the non-metals. We'll discuss that thing as well, right? So we take a kind of average with those two concepts for the non-metal radius, right? So, but for metallic radius, metal atoms radius, we go for metallic radius, right? Directly from that, we can come up with the radii of the metallic atoms, right? So first, we'll discuss about the concept of metallic radius, right? Concept of metallic radius, right? Number one, under the atomic radius, the metallic radius. So it is, as I defined, it is a distance between take the distance between the two metal atoms in your metallic lattice and take the half of that value. That will give you the metallic radius. Let's write the stuff, right? We had discussed, no? Just write the stuff with the metallic radius. Just write. Okay. Under the metallic radius, just write. Metal atoms in a metallic structure. Metal atoms in a metallic structure. Metal atoms in a metallic structure are bonded to each other by metallic bonds. Are bonded to each other by metallic bonds. Metal atoms in a metallic structure are bonded to each other by metallic bonds. Bonded to each other by metallic bonds. Right? Bonded to each other by metallic bonds. Next point. Next point. Half of the bond distance between the nuclei of two adjacent metal atoms, half of the bond distance between two nuclei, half of the bond distance between two nuclei of two adjacent metal atoms, half of the bond distance, just write down, half of the bond distance between two nuclei of two adjacent metallic atoms half of the bond distance between two nuclei of two adjacent metal atoms, in a metallic structure, half of the bond distance between the nuclei of two adjacent metal atoms in a metallic structure is called the come to the red color and write metallic radius is called the metallic radius, right? It's called the metallic radius. So you can write this picture, you can draw this picture, and you can write the metallic radius is actually equal to d over 2. Metallic radius is actually equal to d over 2. Half of this value will give you the metallic radius, right? So we are d is the metallic diameter. D is the metallic diameter, right? Now, this is how the metallic radius is defined or calculated. Just do this one. Just do this one and write this one. This the metallic radius, right? Let's come up with the covalent radius. So some simple concepts, just write this stuff, right? Number 2 is about the covalent radius, right? Covalent radius. Actually, covalent radius is also a simple concept. It is like this. So when two atoms are connected via a covalent bond, see, like H2. When H2, the two atoms are connected via covalent bonds. So you can take it as H2 or Cl2. No? So various things can be written, right? So F2, Br2, the two atoms are connected via a covalent bond. The distance between two nuclei, you can take the distance between two nuclei, this d. And if you have to divide this thing with 2, you get the covalent radius. So that is actually half of the bond distance of a covalent bond. Half of the bond distance of a single bond. Half of the bond distance of a single bond is actually referred to as the covalent radius. So here, actually there is an error. Actually we have an error here, because this overlap, due to this overlap, actually the covalent radius will be lesser than the non-bonded radius. Non-bonded radius means if an atom is without a bond, if your atom is without a bond, That is the radius. This is the radius now. This is an unbounded radius. For the radius we are calculating like this is actually lesser than this non-bounded radius. So that is the problem we are having with the covalent radius, right? Anyway, that is how we calculate the covalent radius, by just taking the bond distance, covalent bond distance, and dividing it by 2. That is how we calculate the covalent radius. And remember, we have problem there. We have error there because of this overlap. So some of the distance is minimized with the overlap, right? So that covalent radius will be smaller than an unbounded radius then, right? So those are the things we should know about the covalent radius. So basically it is the half of the covalent bond distance of a single bond, right? So like that we can come up with the radii of nonmetals, right? Okay, let's write the stuff, and after that we can draw the picture. Just write this here, right? A chemical bond is the attractive interaction. A chemical bond is the attractive interaction. A chemical bond is the attractive interaction between any two adjacent atoms. In a molecule. A chemical bond is the attractive interaction between any two adjacent atoms in a molecule. Right? Okay. With the next line, just write. The bonding atomic radius. This thing is also referred to as the bonding atomic radius. The bonding atomic radius within brackets covalent radius. The bonding atomic radius within brackets covalent radius, close the brackets, for any atom in a molecule is covalent radius for any atom in a molecule is equal to half of the bond distance within brackets you can write the distance between two bonded atoms. Half of the bond distance, within brackets you can write the distance between two bonded atoms, right? So you can draw this picture, right, and write like this, right? Covalent radius is actually this d over 2, right, where this d is equal to the covalent diameter. Or one can write it is actually the half of bond distance of a single bond. Half of the bond distance of a single bond. Single covalent bond is better to write. Single covalent bond. So you can put some examples as well. The H2 molecule is used for the calculate the for the hydrogen. Cl2 is used for calculate for the chlorine. So normally for oxygen, to calculate for oxygen, we are not going for the O2 molecule, but we are going for the H2O2. We are going for the H2O2 to calculate the covalent distance for the oxygen. And we are going for hydrazine, molecule hydrazine, to calculate the covalent diameter, or the to calculate the covalent radius for nitrogen. We are not going to going for O2 or N2, because the when it comes to O2 you don't have a single bond. When it comes to O2 you don't have a single bond. We need to come up with a single covalent bond. If you are referring to the double or triple bonds, the error will be high. Right? So there is an overlap with the double bonds and triple bonds. The overlap will be high. So the error will be high. So that we are not going for double bonds and triple bond situations, right? To calculate the bond distance here, it should be a single bond. So that we can't use O2 molecule to calculate the covalent radius for oxygen. We can't use N2 element for the calculation of the radius for the nitrogen. So we go for H2O2 and the N2H4. H2O2 and the N2H4 for calculate the covalent radii of oxygen and nitrogen respectively, right? Right, because that with the multiple bonds, the error will be high as overlap will be high, right? Okay, just write this thing quickly, complete the picture. Right now, okay. So you can take a screen capture as well, right? Let's continue. Right. See, under next line you can write under the covalent radius. You can write like this: the bonding atomic radius within brackets covalent radius. The bonding atomic radius within brackets covalent radius. The bonding atomic radius within brackets covalent radius, close the brackets, is smaller than the non-bonding radius. The non-bonding atomic radius is smaller than the non-bonding atomic radius. Is smaller than the non-bonding atomic radius. I have already discussed about that thing, right? The non-bonding atomic radius. So this is smaller than that. Right, this is more than that because due to this overlap, right? So bonding atomic radius, the covalent radius, is smaller than the non-bonding atomic radius, right? Within brackets, just write this thing. Within brackets, just write Van der Waals radius. Van der Waals radius. So Van der Waals radius is one kind of non-bonding atomic radius, which we going to discuss next. Is the Van der Waals radius. It is kind of a non-bonding radius. We'll discuss about that thing as well, right? So anyway, the covalent radius is smaller than the non-bonding atomic radius. Some example is Van der Waals radius, right? Okay, right. Let's come up with the concept of Van der Waals radius. Right. Okay. The third thing, right? Van der Waals radius. The third kind of atomic radius under the atomic radius, no, sorry, under the atomic radius. The third kind we are going to discuss is Van der Waals radius. Van der Waals radius, right? So we had seen some error with the covalent radius. We had seen some errors with the covalent radii when it comes to nonmetals. So we should come up with another method, some good method to get the exact value. For that, to get the correct value, right, we use the help of Van der Waals radius too, right? It's the kind of this. So if you are referring to kind of molecules like I2, right? If you are into I2, right? Molecule I2. If you are into molecule I2, this is the concept, right? This is I2. You have one iodine atom here, another iodine atom here. So this thing, this value divided by 2 is what? Covalent radius. Right? It is with an error. It is with an error. Right? So what we do is, we go for something called Van der Waals radius. It is like this. When it comes to solid I2, when it comes to solid I2, solid I2 means what? Solid I2 means the I2 particles are closely connected. This is one I2 molecule, this is another I2 molecule. The two I2 molecules are closely connected. That is solid I2. Solid I2. In solids, our particles are very closely bound to each other. In gases, the particles are very far away from each other. In solids, the particles are very closely bound to each other. This is another I2, right? So, the Van der Waals radius is actually this. Van der Waals radius is actually this. When you are referring two I2 molecules, right, with their closest arrangement, with their most closest arrangement, the distance between two nuclei of non-bonded iodines, these are the bonded iodines, these two are bonded to each other, but these two are non-bonded. You don't have a bond between these two iodine atoms. These iodine atoms are bonded, these iodine atoms are bonded, but no bond between these two iodine atoms. So when they are closely arranged, the distance between the two non-bonded iodine atoms is referred to as the Van der Waals radius. So this D dash over 2 is your Van der Waals radius. Van der Waals radius. That is the idea. So you see, there also you are with an error. There also you are with error. Very simple error. Very simple error. But if you need to come up with a better value, what you need to do is just add the 2 and divide by 2. Just add the 2 and divide by 2. Because you are with a lower value than the exact value here. As with this overlap, you are obtaining a smaller value than the exact value for the radius from the covalent radius. With the Van der Waals radius, you will obtain a greater value than the exact value, because this gap is also included. So you will get a greater value than the exact value. Okay, so you can draw this one, complete the structure, right there. So remember, always the non-bonded radius is greater than the covalent radius, or the covalent radius is smaller than the non-bonded radius. Just keep it in mind, right? Okay. right? This is the idea. So I'll write this in here if you need, right? For I2 this value is, for I2 this value is given as 133 picometers, right? For I2 this value is given as actually 215 picometers, right? So some greater difference is there between the values. So just for the comparison, I have given the values. No need to memorize these values, right? Just for the comparison. Always the covalent radius is smaller than the van der Waals radius, which is kind of a non-bonded radius. You don't have a bond between the two atoms here, right? Okay, that is the idea. Right, that is all about the concept of non-bonded radius. Right. So with the use of these three methods, the metallic radius, covalent radius, and the van der Waals radius, with the use of these three methods, the scientists have calculated the atomic radii of the period tables, of the atoms of period table, right? So those values are given in your note at the as the next part, right? They have given you the atomic radius values, actually which is calculated using these three techniques. For the metals, they have used the metallic bonding, metallic radius concept. For the non-metals, they have used the covalent or the van der Waals radius concepts. Basically, the summation of those things, right? So the average kind of those things, right? So with those, they have came up with the values, and let's discuss about the patterns appearing with the values they have obtained for the atomic radii in your period table, right? Let's discuss a bit about the patterns, right? What kind of patterns are appearing with the atomic radius, basically along the period as well as going down the group, and we'll discuss about the reasonings as well for those. Right. So if you are to go to the numbers there, you will see going towards right of a period, you will see the atomic radius decreases like this. The numbers, the values, the picometers numbers decrease going towards right of a period. And you will see the numbers increases going towards down a group. Going down a group, you will see the atomic radii values increase. That is the common trend you see with the atomic radii values given there in your period table, right? So we can see what are the two observations. Going towards right of a period, right? Atomic radius decreases. Right? So going down a group, for any group you can see the same thing. Going down a group, atomic radius increases. Let's discuss about the reasons for these. Actually, reasons are very clear. Why is that? This is because of increasement of the effective charge. We have discussed about that thing earlier. That is because the increasement of the effective charge going towards right of a period. You see, the effective charge has increased going towards right of a period, so that the valence electrons feels much greater charge from the nucleus, so that they will attract heavily towards the nucleus, making it a small atom going towards right of a period. So going towards right of a period, the atomic radius decreases. What is the reason? Because effective charge Definitive charge is a DFF increasement. That is the reason. That is the reason. Going down a group, nothing happens with the definitive charge, right? Going down a group, nothing happens with the definitive charge. So, what would be the reason for the increasement of the atomic radius? For the increasement of the atomic radius, what would be the reason? The reason is actually the increasing the number of electronic shells. So, with the second row, you are with only 2 electronic shells. With the third row, you are with 3 electronic shells. With the fourth row elements, n equals 4, you are with right? You are with 4 electronic shells. Right? You are with 4 electronic shells. See? So, going down a group, as number of electronic shells where the electrons occupy will increases, so that the atomic radii will increase. That is the reason. That is the reason. Right? Number of electronic shells where electron resides increase. Right? One can say another way, one can say the principal quantum number of the valence shell. The principal quantum number of the valence shell increases. Here the principal quantum number is 2. Here the principal quantum number is 3. Here the principal quantum number is 4. One can say like that also. The principal quantum number of the valence shell increases. That is why the atomic radii increases going down. Or one can say number of electronic shells increase. That is why the atomic radius increases. Both are acceptable reasons. Both are acceptable reasons, right? So that is mentioned here. So principal quantum number of right outer electrons increase, or one can say number of electronic shells increase, right? So that is the reason why the atomic radii increases going down. So those are two trends, right? This is the periodic trend going towards right, the atomic radii decreases. This is kind of a trend going down a group that will increase. The reason should be known. Right? So if you are to draw this as a diagram, if you have to come up with this as a diagram, it would look like this is the radius. And you can take this one as the atomic number. Right? As a diagram, the atomic radius trend would be like this. At the first group, you have the maximum value, then it will gradually decreases like this. Right? The atomic radius gradually decreases like this. Then, so this is 2, 3, 4, 5, 6, 7, 8. Right? Going towards right, you have 8 elements. The atomic radius gradually decreases. When it comes to the next period, again, you will see some greater value with the atomic radius. So atomic radius decreases. When it comes to the next period, the value will be high. Again starts to decrease, going towards right of period. With the next period, again the atom becomes larger. So this kind of trend we would see with the atomic radius. Right now? Going along a period, the atomic radius gradually decreases. Going down a group, atomic radius gradually increases. If you are to say this as lithium, the first group of that row period. For the next group, it is sodium, this potassium. So you clearly see atomic radius gradually increases, going down a group. This is the last element, neon. This is the argon, last element of the third period. So here also you see going down a group, atomic radius gradually increases, right? So that is how this trend appears in a graphical form. In a graphical form, this atomic number. Right now, so it is better to draw this thing as well, right? Better to draw this thing in the gaseous form, in a graphical form, right? So the last two values are like this, right? The first two values are like this for the hydrogen and helium. This is how the atomic radius thing appears.